let's give Ben a chance for some extra credit, shall we? We're going to call this the game show host problem, all right? Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, goats. Which door would you choose, Ben?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a goat. Now, Ben, game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2? Now, is it in your interest to switch your choice?
Yeah.
Well, wait. Remember, the host knows where the car is, so how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat?
Well, I wouldn't really care. I mean, my answer's based on statistics, based on variable change.
Variable change, but he just asked you a simple question.
Yeah, but she changed everything.
This is the Monty Hall problem. The protagonist Ben solved it easily and effortlessly based on statistics and variable change. He focused solely on how the probability of winning the car changes as the variable changes. He identified how it turns into a game of choosing a certain number of doors out of 3. Originally, Ben chose door number 1, and the probability of winning the car was 33.3%. This is because it's a game where you choose one out of 3 options. Then the host opened door number 3, revealing a goat behind it. Now the car is either behind door number 1 or door number 2. Even with simple reasoning, if Ben switches his choice now, the probability of winning the car becomes at least 50%. It becomes now a game of choosing one out of 2 options. The probability changes as the variable changes. However, here's the catch. If Ben decides not to switch his choice, the probability remains 33.3%. The act of opening door number 3 doesn't affect the original probability of his initial choice. The surprising part is that the actual probability of winning the car when switching isn't 50, but 66.7%. Imagine Ben switching from door number 1 to door number 2. How many doors are effectively opened now? 2 doors. Opening door number 3 by the host is like Ben opening it along with door number 2. It becomes a game of choosing 2 out of 3 options. Thus, the probability rises to 66.7%, which is twice the original probability. The change in variables has been leveraged to gain an advantage. Still not convinced? Try it out for yourself. The more you experiment, the more you will see that the probability of winning when you switch is twice as high as when you don't switch. Sometimes mathematical intuition could give you a new car. May math bless you.